I solve, I done did it well. This is 2579, count total number of colored cells. Okay. There exists an infinitely large two-dimensional grid of uncolored unit cells. Okay. Kind of a strange thing to say, but all right, there's this infinite grid. You are given a positive integer n, indicating that you must do the following routine for n minutes. At first minute, color any arbitrary unit cell blue. All right, so you just pick some cell in this infinite grid, right? And you color it blue. And then every minute thereafter, you color blue every uncolored cell that touches a blue cell. Below is the pictorial representation of the state of the grid after minutes 1, 2, and 3. Okay, so this problem kind of makes this weird, confusing claim to just state that we're coloring a cell and then we go outwards. This weird, like, infinite thing is just to kind of establish that there's no, like, boundaries, right? There's no edges to this system. You know, you color one cell and then every minute you color every cell that cell touches. So it doesn't really state it, what it means to touch a cell, right? But it kind of establishes it in this pictorial graph, right? Because in minute 2, what cells does this cell touch? Well, it would kind of be like your neighboring cells if you were dealing with breadth first search, right? Not this one or this one or this one or this one, but the ones that are adjacent to it, right? So your directions, you have your up, your left, your down, your right. Those are the cells that you can touch. So in minute 2, we would touch this cell, in this cell, in this cell, in this cell. Now, like breadth first search, right? This is basically breadth first search. Now we look at all of the cells that we can touch from this state. Well, I can touch this cell, and this cell, and this cell. We'll do it in a different color so it's not confusing, right? So this cell, this cell, this cell, this cell, this cell, this cell, and this cell, and this cell, right? So this would be minute 3. And it just keeps going like this. So if you wanted to do minute 4, you could do this cell, and 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 this cell, this cell, and this cell. Okay, so for this problem, you may feel inclined to say, well, since I'm literally just kind of doing breadth first search, right? That's what this is. Breadth first search, the idea where, you look at everything on the queue and you add all neighbors. We could just run breadth first search for the size of n for n minutes, right? So it's really n phases or n levels of breadth first search, and then count the total number of cells that we look at. And I guess if we looked at the constraints, 10 to the 5, if we did 10 to the 5 levels of breadth first search, it's going to get big pretty fast. And there's a faster way. All that to say that there's a faster way. Claiming that you could use breadth first search to determine this answer indicates a lot to your interviewer, right? That you can think intuitively, you can apply data structures and algorithms that you've have experience with prior, but it may be better to first state that, but then establish that there's actually a constant solution. I mean, not constant, but there's a closed form solution. There's an equation that you can use to determine the number of cells you touch using this approach after n minutes. Okay? So in order to do that, the best way to figure it out is to just kind of walk through the system. So n equals 1, n equals 2, n equals 3, etc. So for n equals 1, right, you can just touch one thing. For n equals 2, you take n equals 1, and then you add 4 neighbors, right? So this is n equals 2, and here there's 5, right? 1, 2, 3, 4, 5. And then for n equals 3, we're going to take n equals 2, of course. And then we're going to add its neighbors, so everybody that can be touched from this point. And this is n equals 3. And how many is that? Well, n equals 2 is 5. So this is 6, 7, 8, 9, 10, 11, 12, 13. So it's 13 here. Okay. And then we're going to take n equals 4. All right. So we're going to add all the neighbors to this thing. And I think this should be enough to kind of establish something about how this is supposed to work. Okay, so for n equals 4, we have 13 plus 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 plus 12 is what, 25? Right. So what you'll kind of notice here, now this is kind of how I found the answer, and it might be a little counterintuitive to you. Maybe there's something that's far more obvious that you'll utilize to figure out what the closed form equation is. But what I kind of noticed looking at this, it's just totally random and maybe not helpful for you. But when n equals 3, you have this like 3 by 3 square, sort of. What I mean is like you have these edges. It's kind of like a 3 by 3 square, but turned, right? So then here you have for n equals 4, you have a 4 by 4 square. And you'll notice that if you did n equals 5, just for the sake of argument, you'll notice that n equals 5 is what? If I took this was n equals 4, right? So this was n equals 4. And then if I did n equals 5, what'll end up happening is you'll end up having a 5 by 5 square, right? Because all you're really doing is you're just increasing the length of these like sides, right? The problem is it's not exactly a 5 by 5 square, which we'll articulate in a moment, but now you have like a 5 by 5, right? Because every time you add an additional neighbor, all that ends up happening here is this gets increased by 1 all here, and then all the neighbors within here get added, right? So it just adds 1 to that length, right? So if it's n equals 3, it's this 3 by 3 length side kind of diamond, I guess. If n equals 4, it's a 4 by 4. If n equals 5, it's a 5 by 5, 6 by 6, and so on and so forth, right? And you could probably make some sort of inductive argument about that. I'm just going to do kind of a hand wavy, establishment of that fact, right? So n equals 4 here. Now, what we can do is, well, I'm saying this is like a 3 by 3 square, right? But it kind of is, but it kind of isn't, right? Because a 3 by 3 square would be 9, but this is 13. Why? Well, because if we drew a 3 by 3 square, it's like this, right? But when we look at it in comparison to what's on top, you'll notice that, well, this 3 by 3 square is different because it's the 3 by 3 square with, if we took these three and we try to draw out the 3 by 3 square using the components, what you'll notice is, well, if we took this and we try to convert it to this, basically, if you try to draw out a 3 by 3 square as a diagonal, you'll notice that it's missing these center components, right? If we took this 3 by 3 square and we try to turn it over to its side, it looks like this, but there's these holes on the inside, right? And we did the same thing with n equals 4, right? If I took n equals 4 and said, okay, well, this is a 4 by 4, this is a 4 by 4 diamond shape, right? But if I did a 4 by 4 square, right, 4 by 4 square, you'll notice again that it's like if there's a hole, right? There's missing components. So if we drew it as a 4 by 4 diamond, right, put the components on their side like this, there's all these holes on the inside, right? Right, so I'm still missing components when I think of this as in terms of a square. But what I just noticed when I did this problem a few times is, well, this is kind of weird. Look at this. Where all the holes are, you can fit that in there. Notice, so if I want to make an n equals 4 diamond shape, I can take an n equals 4 square, and then I just draw it differently, but notice there's the same number of x's. And then for all the holes, I just put in an n equals 3 square. And I get that diamond shape. And you'll notice for n equals 3, for all the holes, if I took an n equals 2 square and turn it into this diamond shape, coincidentally, not coincidentally, but turns out that that too just fits inside. So that's all to say that, well, it looks like for whatever reason, I've just stumbled upon the fact that for this diamond shape, right, the equation of a diamond shape is, well, the number of grid cells it covers, right? The area that it covers is, well, it's for a square, and then you add in the square of one size smaller, right? So for n equals 4, what we took was the area of an n equals 4 square plus the area of an n equals 3 square. So for n equals 4, it equals n squared, right? Because that's the area of a square of size 4, plus of length 4, n minus 1 squared, right? Because for 4 and 3, so this would be 4 squared plus 3 squared. And I think that might just be the generic equation for the area of a diamond. Maybe you know the equation for the area of a diamond, right? But what I'm basically just saying is, you know, I didn't know what it was, but I discovered it by just kind of drawing out examples, right? Sometimes that can be very effective. It can be very effective to just like look at something, see what it looks like, draw out a few examples, and then see how they relate to each other. Sometimes it just comes to you and it tends to be just luck. But for this, I think it's just the equation of a diamond. Someone in the comments might correct me and say, no, that's the equation of this shape. It's been a long time since I've taken geometry, right? But the essential equation is, well, it's really just the area of the square of that size plus the area of the square of size of that square minus 1, right? So for n equals 4, I add in the 4 square and I add in the 3 square to get the solution. So that indicates to me that the generic equation is just this here, right? So we just return the square that corresponds to that diamond plus a square that's one smaller to fill in those gaps, right? All right. Gang. Cool, guys. So what's the space and what's the time? So for space, it's simple, right? We're not creating any additional variables. We're taking the variable in, we're doing calculation, and we're returning it. So that's big O of constant. And then for time, well, we just do 2 operations based on n. So log n, right? Or what is called O1. O of 1. All right, guys, peace out.